So we will be welcoming very soon. Okay, let me introduce him first. Ron Folman. He will be our second keynote of the day. Okay, so Ron is a professor at the Ben Gurion University. He's the founder and first director of the Center for Quantum Science and Technology at the Ben Gurion University. He's also the founder and first director of the corresponding nanofabrication facility. I mean, for me, it's quite impressive to see, I mean, the pedigree of Ron, okay, because I mean his expertise is ranging from high energy physics to foundation of quantum mechanics, and down to the lab, you know, experimental facility of studying, I mean, atom chips for the quantum optics, down to the nanofabrication facility. So for me, it's always, I mean, impressive to see such scientific research, I mean, a wealth of expertise, okay. So let me mention to you that Prof. Folman was awarded the Willis Lamb Award for Laser Science and Quantum Optics. Okay. So today, I mean, Ron will talk about interferometry on atom chips. So Ron, the floor is yours.
Yes, thank you, Christian, for this kind introduction. Thank you very much to the organizers for inviting me. Today, I'll speak about metal wave interferometry with emphasis on Stern-Gerlach. So it's a weird kind of interferometer. It's not the usual light-based atom interferometer. And somehow it's timely because we're just celebrating 100 years to the Stern-Gerlach experiment. So it's nice to see what has become of their seminal work. So I will be talking about atom chips, and here in the middle you see a picture of an atom chip, some interference patterns of atoms, and I will explain all these pictures as we go along. So as I said, it's now 100 years to the Stern-Gerlach experiment, and actually they went into their lab in Frankfurt in 1919. So 2 years ago, it was the 100th celebration, and there was a big celebration, a big fest in Frankfurt in the original building. For me, it was very moving to be there in this celebration. And you see here actually the building below. Actually, let me put my laser pointer on. So you see here the building that still stands. And of course, Otto Stern later got the Nobel Prize. Here you see Stern and you see Gerlach, and in the middle you see Lisa Meitner. I was actually told that she was nominated for the Nobel 48 times. She never got it. It's one of those interesting historical facts. So, of course, you all know about the cigar story that helped Otto Stern see the signal eventually. And you might think from your textbooks that the Stern-Gerlach apparatus is something simple, but for the last 100 years, people have continued to write papers about the Stern-Gerlach apparatus. I give you here just one example, some very smart people that wrote in 1987, interesting paper about the theory of the Stern-Gerlach apparatus. It's not as trivial as it is explained to us in the undergraduate textbooks. And still on the archive, you see papers coming out. I will not go over them, but quite a few papers about things that are untapped potential, I would say, claimed to be untapped potential of the Stern-Gerlach experiments. This is one example. Here's another example of things that came recently out. The outline of my talk would be a quick reminder of what is the atom chip, what is Stern-Gerlach interferometry, what is clock interferometry, which we did based on the Stern-Gerlach interferometry, some spin-offs like the geometrical phase that appears, and then an outlook, if time permits, on quantum gravity, which is the next thing we intend to do with our Stern-Gerlach interferometer, namely not do it with atoms, but actually do it with nano objects. Around, you see some pictures from the desert around my university, which is about 1 hour south of Tel Aviv, actually surprising a lot of wildlife. At the bottom, you see sometimes I take my students for hard hikes in the desert, or sometimes flying. For some reason, I still don't know why. They never ask for a second flight or a second hike with me. I'm still investigating that. I will not talk today about technology at all, about quantum technology, but of course, all of us are interested in quantum technology. So I just want to flash at you also some quantum technology devices that we're building in our lab. So this is a compact cold atom clock with a pyramid mott that you see here that we recently delivered to the industry. Here you see a real picture of how the mott looks like. Only one of these clouds is real. Here you see handheld, all optical, that's fiber in, fiber out, magnetic sensor, atomic magnetic sensor that has been delivered to the Israeli aerospace industry. Here you see NV centers imaging the magnetic field of vortices in a superconductor. So these are vortices in a superconductor. I really like this image. And what you see here on top on the right is the collaboration of optical clocks, optical frequency clocks in Europe. And we are part of that collaboration. We're now building an ytterbium, almost finished building a ytterbium optical lattice clock, and we're part of that collaboration. Hopefully the second will be eventually defined by these optical clocks. So the atom chip is really around for now 20 years. I hope everybody knows it by now. This is the artist view of how an atom chip looks like. It's some substrate, let's say silicon, with some electrodes on it. You could have fields, electric fields or magnetic fields or optical fields or microwave fields coming out of these electrodes. This is a conveyor belt, by the way, that was designed by Ted Hench at the time. This is from a paper written by Jakob Reichel from his group in Garching. And this is how it looks like in the lab. You see one real picture of the cloud and then one reflection from the surface, and you see all kinds of electrodes around. The atom chip definition is actually broadening. So for those who started the field 20 years ago, it's beautiful to see how people are using now the atom chips for all kinds of particles. For example, not only ground state atoms, but Rydberg atoms and cold molecules and cold ions, cold electrons. And now recently, we actually started a collaboration consortium to put anti-hydrogen atoms, antimatter at CERN on these atom chips. So for me, it's a nice closure of the circle because it started at CERN for my PhD. And now I hope to go back to CERN with the atom chip for ultra cold particles at CERN. You see here the vision, the technological vision of the atom chip. Actually, this picture is taken from our friends in Southampton. And you have a very, very small vacuum chamber inside a silicon wafer. The whole width of this thing is 500 micron. And you have here everything. You have the pump and you have the particle source and you have the mott and you have eventually the cavity QED, and with fiber or electronics, you get the information out. And these things are actually built already by several labs around the world. And it's really beautiful to see this technological development. We ourselves are giving service with a fabrication facility that you mentioned to a lot of labs around the world. And here you see, for example, 2 ions on our chip in the lab of Ferdinand Schmidt-Kaller. This is the chip. Or here's a chip that went from our fabrication facility to Amsterdam, permanent magnet chip, lattice, on which they loaded atoms. And you see here the fluorescence of this permanent magnet. This went from our fab to the UK, permanent magnet loop for Sagnac interferometer. So we are happy to give the community around the world service for these very advanced chips. And if you're interested more about atom chips, a few years ago, we put this very detailed review on that. So I will not say anything more. I'll just mention, of course, the 2 atom chips already made it into space. One is International Space Station and the other is by the German Space Agency. And these are 2 more chips that we're making that are sort of interesting. One is for the US Air Force. I won't be able to give details about that. I just mentioned it. And this is a chip to catch the anti-hydrogen atom that I talked about before. This is now being tested in the lab of Ferdinand Schmidt-Kaller in Mainz. This is the antimatter factory at CERN where these anti-hydrogen atoms are made. So all this is now being done with atom chips. It's really nice. And in the context of atomtronics, our dream is to make this very close to the surface. What you see here are just potential guides. It's a guided interferometer. So this is a guided loop. With these straight lines are actually tunneling barriers. So everything is CW. It's not loading a BEC, but this is a 2D mott running here and giving you a CW signal with a very high flux through these tunneling barriers. So the signal goes, the flux goes in here, goes into the loop, goes out here. And to do these tunneling barriers, you have to be very close to the surface. Here's an example of fabrication that we already are doing towards this kind of dream. And to test if we have coherence, spatial coherence, very close to the surface, we actually took atoms to a distance of 5 microns from the surface in this experiment. And we have put many tunneling barriers there, and we found actually that they have very good, very long coherence times, very close to the surface, room temperature surface. So this was a big and very nice surprise for us. Okay, so going back to the Stern-Gerlach experiment, we're going to use now 2 very unique features of the atom chip. One is that you can have very high gradients. And I give here a very simple example. With 2 amperes, you get 40 kilogauss per millimeter. So very high gradients, which we're going to use for the Stern-Gerlach effect. And the other thing is we don't use coils. We just use simple wires. So we have low inductance and very quick on-off that can go down to nanosecond. And this is very helpful in doing accurate Stern-Gerlach experiments. Yeah, so if you see the chip here and you run some current, you see the different MF states of the atom getting different momentum from the magnetic gradient under the chip. Okay, so we all know about the Stern-Gerlach experiment. It's essentially a beam splitter. It's a beam splitter, of course, with a twist. And the twist is that you have an entanglement between momentum and spin. And this entanglement, you can already play a lot of games with it. For example, we used this entanglement here a few years ago to build a quantum work meter. This was actually an idea coming to us from a theoretician, the group of Juan Pablo Paz. And this entanglement, very simple entanglement of this beam splitter enabled in one shot to know the whole work function, quantum work function of what went into the system. So already just splitting makes very interesting entanglement. But what made us very curious is the following. This is the plaque commemorating the experiment that stands in the building in Frankfurt. And this is, of course, the result they found. But what they don't tell us in the textbook, in the undergraduate textbook, is that nobody really knew if the splitting they got was coherent. Because to see coherent splitting, you really need an interferometer. What they saw, the 2 spots that they saw could have just as well been statistical mixture. So we were curious if we could prove that this was actually a coherent splitting. And so we looked into the literature. And we were very surprised to see that this is a debate that has been going on for a century. And many people have claimed, theoreticians have claimed that this is impossible. There was no coherent splitting there. For example, this is an argument that was put forward by Eisenberg a long time ago. And these are more recent papers. For example, this paper from 2006 claims that we have to go to cryogenic temperatures because of the coupling with the macroscopic magnets. And this paper from 2015 claims that the superposition is actually forbid continuation of a spin superposition through the Stern-Gerlach field. So many papers are still coming out. And the problem is that people fear different things, but one of the, as an experimentalist, one of the things that I fear is the fact that if we have 2 spins here and they are different trajectories, then they couple differently to magnetic noise. And of course, that's very bad for any interferometer. And so people that have tried previously to do these kind of interferometers put many magnetic shields. This French group really did some heroic experiments, and they put all these magnetic shields because of this worry. And the splitting really is very hard. So what we did is we tried to do it, but this time not with a beam, but with very cold atoms. And so this is what we did. We call it the half loop. And in a minute, you'll see the full loop. Okay, so you just put a spin superposition with an RF pulse. You do a magnetic gradient. This is the purple. You then do another pi half pulse just to mix the spins. Otherwise, you have orthogonality and you'll not see any kind of interference. And then we have a stopping pulse that stops the relative motion. Because of this gradient, the one spin states go out, and we're left with two spin states, and they, over time, they just expand, overlap, and we see beautiful spatial interference patterns, even for thermal atoms. So this was for us the first proof that really, although the splitting was many times the wave packet size, up to 20 times the wave packet size, we could still see very nice interference fringes. And for us, this was proof that indeed you can get coherent splitting. But now the game only begins. And you can play many games with this apparatus here. And the first thing we wanted to do is play with witch path information and complementarity, which of course is a game that people like playing for many years. And we found this paper from the Bruckner group in Vienna, and they talked about clock interferometry. So if you take a single clock and you put it in a Mach-Zehnder interferometer, Mach-Zehnder type interferometer, and the two clocks show a different time because there is redshift and they're split vertically above Earth, then this should be witch path information and you should not get any interference pattern. So we set out to do just that, to take a clock and to put it in two trajectories vertically above Earth. So what you see here actually is that after we did what you saw before, the half loop, we prepared the clock from these two spin states. So each one of these wave packets was now turned into a clock with a pi half pulse. Then we made a redshift. It's a synthetic redshift because Earth's redshift is very, very hard to see, especially in small splittings. And then we again looked for interference patterns. And the theory coming from the Bruckner group, these are the Bloch vectors of the two clocks, two clock wave packets. The theory, of course, that if the time is the same in the two clocks, two wave packet clock, you'll get interference. But if the time is different, of course, you get no interference because time is witch path information. And if you look here at the interference visibility versus the redshift, of course, you start seeing oscillations, which is exactly what theory predicted. Okay, and we went on to define a new clock complementarity rule, which I don't have time to go into. Let me just say that for high spins, it's a very, very strange rule. And mathematically, we still don't understand it. But at least at the level of a spin half, we were able to experimentally verify it. So I welcome if theoreticians look at this complementarity rule, which was published a couple of years ago, and try and understand different things. And this, of course, all has to do with decoherence induced by gravity. And there are also speculations that the complementarity rule will actually break when we really are able to see the curvature or the redshift of gravity. Our clocks would be good enough. So let me skip this. Let me just tell you actually that there is a big debate over the years what clocks, what interferometers are sensitive to proper time and what are not. And we're lucky that the Stern-Gerlach interferometer is sensitive to proper time. Okay, a very beautiful spin-off of this kind of interferometer is something called the non-cyclic geometric phase. So I showed you before the two Bloch vectors of the two clock wave packets. It's one clock, but two wave packets. And apparently, we're all used to the fact that for a geometric phase, we have to close a circle on the Bloch sphere. But there is something called a non-cyclic geometric phase. It's enough that you close one line. So you move one wave packet, you have two wave packets here, and then one wave packet you took here along the latitude. The geodesic already closes the area for you. You don't need to do it yourself. So that was actually surprising for me to learn. And we actually observed this area. And what happens is, as you take the clock down through a theta of 90 degrees, you go through the equator, there is a jump here of sine. And actually the area is maximized when you go down and suddenly it flips sine. So there is some kind, it's almost like a phase transition here where a positive large area turns into a negative large area, and you'll see it a minute in the data. So anyway, this all has to do with the Pancharatnam phase that goes back to 1956. And of course, the Pancharatnam phase, if you take into account the dynamical phase, is also the geometric phase, which we all know and love. And so if we look at the data, this was the prediction actually we found in 1991. This is the simulations, modern simulations, it's exactly the same. What happens here, this is the theta angle that I told you about going through the equator. And what happens is when we scan that theta, we get these jumps. Okay, this is just the phase of the interferometer. So you see, if you see on the left and you see on the right, this was a pi phase jump. And so these are these sharp jumps of the Pancharatnam phase and these very sharp jumps of the geometric phase. Okay, these are theoretically infinitely sharp jumps. So we were very satisfied to see that actually we see this very nicely. There are many spin-offs that you can learn in these interferometers. For example, here we see something we call periodicity, rigidity. This is just the periodicity of the double slit experiment, if you like. And here we change, if you like, the distance between the slits or the lambda of the radiation or the matter waves, and you expect to see some kind of continuous monotonic change line. No, we see rigidity. So we change the parameter of the system and the periodicity on the screen does not change. You can now find it on the archive. We call it observation of anomalous moire patterns. And it's just another artifact of very interesting effects, which I don't have time to go into. What I do want to go into is the full loop, which is the hardest thing to do. I showed you the half loop until now. But the half loop is like a double slit experiment. The wave packet expands. Actually, when wave packets expand, they increase the local coherence length, which gives you, it's actually easy to see interference pattern. But if you do a full loop and you force them back to a full overlap of momentum and position right here, it's very hard to do because this is now dependent, the contrast here is dependent on the what's called the overlap integral. You have to get the momentum and position to overlap completely. And this has never been realized. And although people have been dreaming of this for many decades, and I think Bohm is the first one to actually put this picture on one of his papers. And the problem is really time reversal or time irreversibility. The second two magnetic gradients, you see here two magnetic gradients, they have to completely undo the operation of the first two magnetic gradients. So here is a magnetic gradient that does splitting, stopping of the relative motion as we had in the half loop, then accelerating back, then fully stopping the relative motion. And so these two have to completely undo the first two, and you want to get exactly with fidelity of one, the same wave packet with which you started. Okay. This is very different from the very accurate light-based interferometers that we know and love, because there the momentum transfer has a quantum accuracy. But we're dealing with classical fields of classical magnetic fields. We don't have the 2h bar k classical quantum accuracy of the light transfer. So this is a very interesting question. How far can it go? Okay, so many theoreticians talked about it. Heisenberg, Wigner, Lamb, Bohm, Fermi, many people. There were many debates, but in the 80s, it was quantified by Englert, Scully, and Schwinger, who actually called it the Humpty Dumpty effect, because they claimed you need ultra high precision of the magnetic fields to actually do it. And the equation they put is this. So if your experimental imprecision in putting back the momentum together of the two wave packets, and if your experimental imprecision of putting back the position of the two wave packets is not smaller than the original uncertainty in position and momentum of the wave packet, original wave packet, you're going to have an exponential drop in your coherence. So this is a very hard equation to fight, yeah? And so, and of course, many papers are talking about the time reversal and so on of this problem. So we went to do the full loop. So instead of two magnetic gradients, we now go and do 4 magnetic gradients, as I showed you before. Now, instead of letting the two wave packets now expand and give a special interference pattern, now the two wave packets are brought together. You don't have a special interference pattern. You now look at the spin. So your signal is now the spin, and you expect, if you have good coherence, to see oscillations in the spin. Okay, so we set out to do that, and lo and behold, we're very happy to see that we got a very high contrast of the spin fringes also in the full loop interferometer. Okay, so now we could play some games, and we were very lucky to be approached by the group of Wolfgang Schleich in Ulm. And his group, including Maxim Efremov and Matthias Zimmermann, theoreticians who liked the idea of the Stern-Gerlach full loop, and they remembered that many, many years ago, that's 1927, almost 100 years ago, Kennard thought about the problem. And he said that if you actually put an atom or a particle in a continuous linear potential, you're going to get a very strange phase accumulation. And that is going like t, the time of the potential, or the interferometer in this case, to the power of 3. Now, this is very strange because if you look at normal interferometers that we have, like the Ramsey-Bordet or the Mach-Zehnder, they go like t to the power of 1 or t to the power of 2. So t to the power of 3 is very strange. And I will skip the theory and just tell you that eventually what you see here is that the phase goes as t to the power of 3 if td, which is this separation, dead time between the pulses, can be taken to 0. So we made the effort and we took this dead time to 0. So we're only left here with a t to the power of 3. We were very happy to see this is the theory from Wolfgang Schleich's group, and the data sits beautifully on this t cubed theory. And then people started to wonder what you could do with this t cubed, and there, about a year ago, there was this paper by Chiara and Vlatko, who actually told us that this t cubed could already be used to look at quantum effects of gravity. In this case, they were talking about the equivalence, specifically quantum nature of the equivalence principle. So this t cubed phase apparently has very interesting potential. But the experiment we are actually really dreaming of doing, and with this I will conclude my talk today, is taking this Stern-Gerlach full loop that I just described to you and putting nano objects in it. So if you could take something, a diamond, a nano diamond, say with 10 to the 7 to 10 to the 10 atoms, yeah, and have just one spin embedded in it. It's just like an atom, but it's a very heavy atom. So it's just like our rubidium atoms, but with a single spin. But these rubidium atoms now have a very big weight attached to them. So these ideas are already at least 5 years old. There is this very interesting paper that came out in 2016 by these people, and they were already picturing here the full loop. What you see here is a full loop Stern-Gerlach interferometer for the nano diamond. Again, a spin superposition. The gradients, they split the two spins into two wave packets, and then they bring them back. This is active recombination, which is the special thing about the full loop. We do active recombination, which again has to be time reversal symmetry, has to have time reversal symmetry, and then you take a measurement of the spin. The question is, can this be done? Very hard experiment. We are now conducting feasibility studies on this experiment. They don't even want only one Stern-Gerlach loop. They even want two Stern-Gerlach loops, one next to the other, and then looking at the gravitational interaction here that you see between two wave packets. So there are a lot of far-reaching dreams of what you could do here. There are several feasibility studies out there. One is just being published these days, and the other one is on the archive, written by Ryan and Anupam and Sugato. You see them also on this paper up here. And actually, we were very happy that also Physics World took up the story and reviewed this idea of putting a nanodiamond into this Sterngerlach. If we will succeed in doing that, we owe many, many thanks to a lot of groundbreaking works that have happened in the last few years. For example, the group of Marcus Aspelmeyer with their ground state cooling. You have to have very good ground state cooling to get enough coherence length to fight the exponential decay of the Humpty Dumpty. I showed you that at in the exponent appear the momentum width. This is the coherence length, and you have to fight it. So this ground state cooling is going to be essential. And also people that are like Ben Stickler and Lucas Novotny, who are talking about ground state cooling of the rotational degrees of freedom, that is essential also for this success of this experiment. And of course, people who have done beautiful things with nanodiamond recently, like Gabriele Tet, who has done beautiful trapping and manipulation of nanodiamonds. And so all these people we will have to thank if we're able eventually to get this experiment to work. So we will have time for questions. I will be happy to answer many questions, especially on the nanodiamond, which is right now exciting us very much. So I hope I convinced you that the Stern-Gerlach effect is far from completing its historical role. There's a lot of undiscovered territory, and actually we are finding out new things. I don't want to say on a daily basis, but people are approaching us with new ideas all the time, and it's really fascinating. And there's several possible impacts on the study of gravity, and actually didn't tell you much about how we're going to do this experiment with the nanodiamonds. But actually in 1 hour, I'm supposed to give another talk in another conference. It's called Gravity in a Lab. And if you are interested in details of this experiment, you're welcome to come to this workshop and hear the details. And a lot of details have been put recently by us in a chapter in a book in honor of Otto Stern. This book is just out by Springer. Many thanks to Mark Kyle, who actually wrote this chapter. And so there are a lot of details on what I have been speaking about today here. And of course, thank you to the team. There are people who worked very hard to get these experiments going. These experiments, because of the Humpty Dumpty effect, are very hard to realize. As you see here, a lot of people have already left, and now Or is in charge of the experiment, and he will be going forward to it. And of course, thanks to the many theoreticians that have helped us along the way. That's it. Thank you for your attention.
Thank you very much, Ron. Okay, just, I mean, a brief mention. Okay, I was thrilled, and I'm really in awe with all your results, and I hope I can visit you in Ben-Gurion University. You might not know, because I mean, my name was not on the publication, but I was part of this heroic team who did the experiment in Villetaneuse with Jacques Baudin. In fact, I was the one who started that with Jacques Baudin at the time. So, and this is how I met Berger and Glert, because we wanted to discuss the Humpty Dumpty effect back in '92. And this is how I ended up in Singapore in the end. So you see, and now I am chairing this session. So I mean, really wonderful for me. I was really in awe. So, and I hope I can visit you in Ben-Gurion University.
Great, you're welcome to come.
Okay, okay. So let me open the session for questions. I mean, Luigi.
Yes, thanks for this talk, Ron. I have a couple of questions on, maybe you can explain a bit better. So I understand that making this loop of the Stern and Gerlach experiment is very complicated. So this, I think, is clear from your talk. What is not completely clear, maybe you can comment more, it's why is it interesting to do that? Okay, So, and this is the first. And the second, I'm very, this idea of constructing these two interferometers, okay, to check, to test the gravity. So maybe you can explain what is the so why is it so interesting?
Okay, so one question at a time, we'll try.
Yeah.
Thank you, Luigi, for these questions. So first of all, when you build a new interferometer, you never know what the eventual applications would be. You just want to see how far you can go. How far can the technology in the lab go? And we were curious about that. And as I said, these magnetic fields do not have quantum accuracy. These are classical currents, classical fields. By the way, we're hoping to push in squeezed currents into the atom chip. Then we'll have maybe some quantum accuracy in these gradients. But for now, we have classical gradients, and but they can give a lot of h bar k. They could give a lot of momentum kick. And the jury is still out eventually. What would give you more momentum kicks, stronger momentum kicks? The many photon transitions that people are trying to do to get hundreds of h bar k, but then they start losing contrast as they give more and more photon transitions, or these magnetic pulses, which are not quantum, but have very strong power. So it will be very interesting to know at the end of the road who can give you more splitting. So that might be one application. The other application has to do with this T-cubed phase. The T-cubed phase, as I told you, is unique. By the way, because it's unique, it's also very nice for the nanodiamond interferometer because it will tell us that we're really seeing what we think we're seeing, and not some fake signals from some other kind of evolution, because the T-cube is really unique. And as I showed you here, once you get this T-cube, you can think of all kinds of things. I will not go into them, but for example, this paper that I mentioned by Chiara and Blatko claim that these kind of T-cubed phase are able to give you new insight into the interface between quantum and gravity. You should ask them for details, but it's an interesting paper to read, and I recommend to people to try and read it. So once you have this unique phase, it looks like you can do all kinds of things with it. But the most unique application is this, because if you try to do a nano object with the regular light interferometers, it's almost impossible. Because first of all, you need some optical transition inside your nano object. And you need to go through the whole object for your laser to get to this optical transition, which is in the middle. It's probably very, very hard to do it with a usual technology. So people indeed have been thinking of all kinds of other technologies rather than the usual light-based interferometer, how to go forward and split nano objects and do an interferometer with nano objects. So this is one of those suggestions, how to leave the light-based interferometers and go for an interferometer that is easier or more suitable for these nano objects. And indeed, as I try to show, there's now a growing body of theoreticians and experimentalists that believe that using the magnetic gradient, the Stern-Gerlach force, is the way to go if you want to really have an interferometer of macroscopic objects. By the way, it has different advantages. For example, you're going to have horrible decoherence for these nano objects, not just because of background gas collisions, but you're going to have horrible decoherence because of, for example, black body radiation. And so you want to do it very quickly. Now, one of the things we were able to show about this loop is that this interferometer you can do it, very, very quickly. You have very strong forces, so very quickly you manage to split them, very quickly you manage to recombine them. So I would say that, for example, in 100 microseconds, we can do the whole operation. So you can fight with this kind of strong forces and active recombination, you can fight against the very strong decoherence rate that you expect to get for these kind of macroscopic objects. Another advantage is that at the end, you don't need to have some imaging, some CCD imaging of some special interference fringes, because special interference fringes of macroscopic objects are notoriously hard. Here, you're just looking at the spin. So no imaging, you don't need high imaging resolution, very easy, very easy, relatively easy detection of a spin rather than looking or waiting for far field interference fringes to develop. So this kind of full loop interferometer, you asked what are the advantages? There are many doors that it opens. Yeah, and
the precision would be larger here, right?
The what, sorry?
The precision, the performance of the interferometer would be much larger, right?
No, it's going to be harder than our atomic Stern-Gerlach interferometer, and I'll tell you why. Okay. I'll tell you why. Because we have a certain precision with our magnetic fields. Yeah, actually, with the atomic interferometer Stern-Gerlach, we were able to see that our precision is about, in position, is about 100 nanometers, or rather our imprecision, our experimental imprecision in bringing the two wave packets together is about 100 nanometers. Luckily, their coherence length was larger than that. But if you look at these macroscopic objects, even if you cool them to the ground state of, let's say, a trap of 100 kilohertz, you're going to get a coherence length of 0.1 nanometer. So we have an imprecision of 100 nanometer. You have a coherence length of 0.1 nanometer. So the Humpty Dumpty equation is going to tell you that you're going to have zero coherence.
Yes,
zero. If you want to improve on that, you have to get your whole setup to be much more precise than what we had so far. Yeah. Okay.
I have a naive question, maybe for the T3, phase, right? Okay. The function that you get is the Airy function, right?
You are talking about this function?
Yes, this is the Airy function, essentially.
Well, I never thought about it in those terms, but yeah, maybe you can call it.
To me, when I see the shape, it's an Airy function, and because you mentioned also linear potential or something like that. So I believe there is the Airy function, and to me, the Airy function is also connected to caustics. So is there anything you can think about, about that? I mean, are caustics playing a role? I mean, have you ever investigated that? I don't know if Michael Berry is with us tonight, but he's the expert, I would say, on the matter. Okay.
I would be very happy to hear about it. No, we have not thought about it, and we have not investigated it. By the way, since you asked about this function, let me tell you something about this function. This function, when you put in a nanodiamond, is horrible. And why is it horrible? Because the amount of phase accumulation is horrible. And when you have so much phase, like maybe 10 to the power of 5 radians, you're not going to see anything because your phase jitter is going to kill you.
Yes. Yeah.
So you have to kill these two terms before you can start doing some tricks for getting little phases. And how do you kill these two terms? First, you have to take this interferometer, and do it perpendicular to gravity. So gravity is 0. If you do gravity 0, so it's in a free fall. But you do the Stern-Gerlach forces perpendicular to gravity, so it's a 1D interferometer perpendicular to gravity. This cancels out. Gravity G goes to 0. That's one. Two, if you do it in symmetric spin states, and luckily the NV diamond gives us the -1 and the +1, you get this term goes to 0. Yeah, if you use these +1 and -1, so this also goes to 0. This saves us. if we would not be able to zero this phase, we would be dead in the water.
Killed.
So
Yes.
there's a lot of lucky coincidence here that
Yes,
enable us to
consensus,
think.
yes.
Yeah.
I have another question. Okay, I remember my time back in Wiltanes. Okay, have you thought about producing kind of a non-Hermitian Hamiltonian and study these non-Hermitian topological phase factors?
Well, the answer is no. The short answer is no. The short answer is no. We are still struggling to see something, you know. So we are still just in the first steps of exploring what is there to see. The first game we played was this T cubed, which turned out to be very successful. But aside from that, we have still not investigated further these phase factors in any serious way. By the way, there's a beautiful phase that we're now trying to investigate. That's our next project. And this is something called the separation phase, which you can see in a beautiful way in this interferometer. And it's quite hard to see it in other interferometers. But many people already before wrote about it. But it's hard to really measure it and compare it to theory. I think, for example, the first guy who wrote about it maybe was Mark Kasovich about the separation phase. And this is also something that is very intriguing for us to study with this interferometer. So we are starting to look into different phases that's coming out of this equation.
Wonderful, really wonderful. So then, Ron, let me thank you again. Okay. And hope to see you soon in Ben-Gurion University. Or I'm not proposing that you come to Singapore because you will be trapped for 3 weeks in quarantine, so it's not a nice experience.
Yeah. By the way, I don't know if Peter Zoller is still here, but when he gave his talk, I remembered I was a postdoc in Innsbruck at the time, and there was of course, Peter Zoller and Ignacio and Helmut and many very, very smart theoreticians, and I learned a lot from them. But one of the things that Peter actually talked about in those days was the technology that we need to develop. And he actually, maybe he doesn't know it, but he is one of those who gave me the push to go into the technology of atom chips. And in that sense, I owe him a big thank you for also appreciating that
Thank you.
Deep technology has to be developed.